Good morning, good afternoon, and good evening, everyone. Welcome to today's Ask the Expert webinar on composition and contaminant measurements of solid state materials. Our experts for today are Luke Picard, Senior Scientist, Louis Gillian, Analyst, Venkat Vimuri, Senior Scientist, and our moderator for today, Greg Strassman, Scientific Fellow. My name is Rena Samsu, and I am the Senior Marketing Manager assisting with today's event. Before we get started, let's go over a few housekeeping items. All attendees have been muted. However, if you have additional questions that pop up during the presentation, please submit them in the questions section located in the bottom of your control panel. You may send in your questions at any time during the presentation. Time permitting, we will answer these questions during today's event, or we will follow up with you in the coming week. With the abundance of pre-submitted questions for today's event, we unfortunately will not be able to get to answer all the questions during the presentation. For any unanswered questions, the team will send answers out to those questions soon. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. Now I will turn it over to one of our experts and moderator for today, Greg Strassman. Greg?
Thank you, Rena. Welcome everyone to the next segment of our Ask the Expert series. Today's subject is composition and contamination measurements of solid state materials and will include discussions surrounding XRF, TXRF, RBS, and HFS. A good place to start is an introduction to our group of presenters. My name is Greg Strassman. I have nearly 30 years experience in materials characterization in several areas and will for the most part today be behind the scenes, acting as moderator while collating and trying to answer on-the-fly questions. My colleagues here will be handling the heavy-duty lifting, so I'll let each of them briefly introduce themselves.
Hi, my name is Luke Picard. I've been with EAG a little over a year now, but I also have 15 years experience working on the instrument sector side of things for Bruker in XRF.
Hey, my name is Louis Gillian. I've been with EAG for coming up on 2 years now, and I have over 4 years experience in materials characterization.
Okay, the agenda for today is shown here, and it'll start with a brief introduction to Eurofin's EAG, followed by a description of our SMART chart. Then we'll be turning the seminar over to you. All of these sections have been designed around your questions, so you really are running the show here. At the end of the presentations, we've set aside some time for a Q&A with all of the presenters back online. Eurofins is a global leader in testing with more than 58,000 employees and 900 labs in 54 countries. Eurofins EAG is a division of Eurofins specializing in materials testing with over 40 years experience. We have more than 1,000 employees and 20 laboratory facilities all over the world. We have more than 2,500 different types of testing equipment and support over 5,000 clients. So what industry segments do we serve? A better question might be, what don't we do? Our laboratories have many techniques and experts available that can be applied to the entire life cycle of products in any industry. So now let's take a look at the SMART chart, often referred to as a bubble chart. SMART is an acronym for spectroscopy, microscopy, analytical resolution tool, and it shows the techniques we have at EAG. It allows us to compare the spot size and detection limits of each technique, as well as color codes that indicate the type of analysis provided. It's worth pointing out that this bubble chart is constantly evolving and has grown considerably since its first introduction in the 1990s. Regarding the colors, dark blue bubbles provide primarily elemental information, while green shows imaging information. Orange or red indicates that these techniques can provide some form of chemical bonding information. Note that imaging techniques only require spot size, while bulk analysis techniques are only distinguished here by detection limits. Therefore, these are outside of the box, along with the appropriate axis. Today, as noted, we're covering XRF, TXRF, and RBS-HFS. As you can see, these are all blue bubbles indicating elemental analysis only, and you can see the differences in both analytical spot size and detection limits for the three. So here's another useful chart which shows the depth of analysis of each technique. This is a very important consideration that it's important that you understand. So as you can see, the analysis depths can vary significantly, in some instances by orders of magnitude. We always want to choose the most appropriate technique for the job request, and depth of analysis is an important criterion. It's also worth mentioning that care must be taken when trying to compare results from the same sample, which often we do. We'll do an analysis of different techniques on the same sample. And it's important because the very near surface of a sample may look strikingly different than the bulk matrix. So before we move on to the individual sections, I'll give a brief introduction that also shows the format you can expect, assuming that this is the first time you've attended one of these events. Right off the bat, after the mailers went out, we got several general questions, such as the sampling shown here. For example, how do these techniques compare? When would I use one over the other? So as we go through this, you'll see more in-depth answers to all of these in the individual sections with the other experts. But just to get us started, here's a brief comparison of the techniques being discussed today. You can see that XRF and TXRF have many similarities on the surface. In fact, TXRF, total reflection X-ray fluorescence, is just a specialized application of X-ray fluorescence, XRF. But the differences in instrumentation lead to unique applications of the techniques with little or no overlap. On the other hand, XRF and RBS-HFS are very different in how the measurable signal is generated and what that signal even is, but both share the niche of being excellent techniques for thin film analysis. And with that, I will now step back into the background and turn things over to Luke to address your questions about XRF.
All right, thank you so much, Greg, and thank you guys for all joining us today. Yeah, let's get started. So first off, we had a few questions submitted asking us about the fundamentals of XRF, and also one question asking what are some possible sources of error in XRF measurements. And this is a good place for us to start. So in short, XRF is a method that measures the wavelength and intensity of X-rays emitted by an energized atom within a sample. In XRF, we have an X-ray tube that is sending a primary beam of X-rays towards a sample. Those primary X-rays are going to knock out an electron from one of the orbitals surrounding the nucleus within an atom. This electron needs to be replaced to restore equilibrium. So an electron from a higher energy outer orbital will take its place. This is since this is a lower energy position, the excess energy is emitted in the form of secondary fluorescence X-rays, and each element has a specific energy it emits, which is how we determine what elements are present in the sample. Since the X-ray secondary fluorescence intensities for each element correlate directly to the number of atoms present, we can then determine the concentrations of all those elements. In our other figure, on the right, we show the primary beam hitting the sample. The X-ray fluorescence that is generated is going to come from varying thicknesses within the sample. And as a result, this is our first possible source of error. The thing to note here is that the higher the energy of the fluorescence X-ray generated, the greater the escape depth of that X-ray from the sample. This is a huge reason why samples being analyzed by XRF need to be homogeneous in order for us to get that greatest degree of accuracy possible. To expand on that thought, the escape depths for different element X-rays can vary on orders of magnitude, both in the same substrate, but also all elements are greatly affected by the makeup of the substrate itself. To understand that a little more, let's check out this first table. In this table, you'll notice we're looking at two different types of samples. Not only is the escape depth getting deeper as the energy photon increases, but it also increases when looking at a sample with a lighter matrix, and this is across the board, and this one's silicon oxide. Now, another source of error can come from the fact that fluorescent X-rays of elements close to or adjacent in the periodic table can have complex interactions that affect both yield and depth. Without getting too in the weeds here on this topic, you'll see in our other example, the matrix is aluminum. Even as elements shown are increasing in energy, the escape depth for silica is much lower because the absorption effect the large amount of aluminum is having on it. All right, some takeaways then to bring home with you are the fact that the greater interaction volume or depth we are analyzing from a sample will directly correlate with greater sensitivity. Also, the sample should be homogeneous throughout the analysis volume for XRF to get accurate quantification. Some other questions we received from you centered around common XRF applications. In the pictures, you'll see a few of the industries that XRF is commonly used in, but by no means are these the only ones. One of the great things about XRF is the vast variety of applications it can be used for. Since solid samples, powders, and liquids can all be analyzed with XRF, some common applications include the identification of unknown materials such as powders, debris, and coatings, as well as quantitative compositional analysis of bulk materials and thin films. It is also considered an industry standard for both single and multi-layer films. Trace element analysis in solid and liquid samples is also commonly done, and we have the ability to do whole wafer and sputter target analysis. The XRF instruments we have in-house here can analyze spot sizes from 0.5 millimeters to 30 millimeters in diameter, with larger spot size giving us the most sensitivity. So if you guys ever have a question on how much sample you should send us, we recommend always erring on the side of more so we can get those detection limits you may be looking for, if that's possible. We also have a sample adapter for large, oddly shaped parts available. These next questions we received revolve around quantitative analysis. Some questions include how do you obtain accurate results using WDXRF without having calibration standards, and what is the accuracy of measurements if you don't know the base material? So once a sample has been ran by XRF, at the very least, we're always able to get you a qualitative analysis and know what surface or near surface elements are present. But in most instances, we're also able to get you quantitative results. The two ways we can achieve quantitative analysis revolve around creating a calibration with those matrix match standards or using a fundamental parameters-based software package. Fundamental parameters is going to use algorithms based on pure element standards and X-ray physics to give you a standardless quantification of unknown materials. We commonly refer to this as semi-quantitative. Some typical relative accuracies we see with this method are from less than 1% to 20% for both major and minor elements. Now, if XRF has access to matrix match standards, and we're able to build a calibration curve, you can achieve unmatched accuracy for quantitative analysis. You'll see accuracies as low as 0.1% or better, actually. Okay. Here we see two tables showing the accuracy we achieve in a couple common applications using both fundamental parameters and a dedicated calibration. On the left, we show fundamental parameters. The FP quantification is plenty sufficient for the identifying of specific alloys or glass or ceramic types. It's also great for measuring complete unknowns in research samples. And then on the right, you'll see the high accuracy for when calibrating against standards. I want to just point out both the 0.1% relative accuracy for nickel, as well as being able to reach the 5 to 10% relative accuracy for trace elements in the hundreds of ppms. Even with the range of accuracy being a little larger using fundamental parameters, we shouldn't forget that the precision is actually in the 0.1 to 0.5% relative range, which makes XRF an excellent technique for the comparison of samples such as a good sample versus a bad sample. Okay, as stated earlier, another common application for XRF is non-destructive thin film analysis, and we had several questions regarding XRF's ability to measure these types of samples. The graphic on this slide should look familiar, as it's the same as one I showed previously. This time we're just showing the process where there are films stacked on a substrate. As long as we meet a few criteria, XRF is going to be a great technique to use for this type of analysis. These criteria include that the source X-ray must fully penetrate and excite all the layers. Also, the escape depths of fluorescent X-rays must be larger than the thickness of the films, because without this, changing the thickness will not affect signal intensity. And of course, we need that to be able to measure the thickness. Lastly, the order of the layers must be established to complete the calculation. So we'll need to know that order ahead of time. Okay, here we have some spectra from a thin film sample that was run with XRF. The fact that we have strong signal here coming from copper, the copper substrate, proves that we have sufficient sample depth to measure all three layers. In the table, we show a comparison of some results quantified using fundamental parameters, and then also quantified using certified standards. As you can see, even when just using fundamental parameters, we still get linear and really quite accurate results. The accuracy does definitely increase with standards, especially for those buried layers. All right, last but not least, we received several questions on comparing XRF to other techniques, as well as what method is best for specific applications. And to kind of help answer this, we created a basic chart showing some reasons one may choose XRF or another technique for the same analysis. In regards to XRF versus RBS, we're strictly comparing them for thin film analysis. One advantage as far as XRF is concerned is going to be the significantly larger depth of range for measuring thin films. A limitation is that it is standards would be required in order to get that best accuracy. Yeah, just a general comment. It's often used together with RBS to quantify adjacent elements that RBS cannot resolve. The rest of these comparisons are for bulk analysis. XRF and ICP OES are the most complementary techniques here. They can both be used interchangeably, but unique differences might make one a little bit better in specific cases. One definite advantage to XRF is that it's non-destructive, and it's not going to require digestion of the sample like ICP OES. A limitation you may have is that it's often less accurate when relying solely on fundamental parameters. But if we had a calibration to go off, it's very comparable. Lastly, when considering SEM EDS, which many companies might have access to in-house already, in our opinion, it should only be considered a last resort for compositional analysis, as with XRF, it's just much better quantification accuracy when we consider the significantly better sensitivity and larger depth of range. All right, so in summary, as we discussed, some strengths of XRF is that it's a non-destructive technique, and it has the ability to measure solids, liquids, and powder samples. It's a great technique for measuring thin films, including whole wafer and sputter targets. Now, on the other hand, some limitations may include the spot size needed for your type of sample, and the fact that sample homogeneity is critical for accurate quantification. Thank you guys so much for listening to the XRF portion. I'm going to pass things off to Lewis, and he's going to answer some of your TXRF questions. Thank you.
Thank you, Luke. Hello, everyone. My name is Lewis, and today I'll be answering your questions about TXRF, or total reflection X-ray fluorescence. We received over 70 TXRF questions asking about a number of topics. I'm going to try my best to answer many of them here. So we received a good number of questions asking about some background info about the technique. Questions like, how does the technique work? What can it be used for? What does it offer that is unique? And how does it differ from XRF? So I'd like to give a small introduction to the technique. So like XRF, TXRF is an elemental survey technique that we use here at EAG for semiconductor wafers that can detect what atoms are present on the surface of a sample. One of its unique capabilities is that it is non-destructive technique, which can give location-specific information on contaminants. The fundamental mechanics are similar to XRF, but instead of having the incident X-ray come in at a high angle and probe into the bulk of the sample, with TXRF, the incident X-ray comes in at a very shallow angle, below the critical angle of the material, which is our material is about 0.05 to 0.5 degrees. And then for those curious, the critical angle is the angle at which you start to see refraction into your material. By coming in at a shallow angle below this, this limits the excitation to the surface of the sample, which is about the top 30 to 80 angstroms of the material. And because the X-ray beam is totally reflected, this reduces absorption and scattering in the sample matrix and leads to increased sensitivity. So with regards to sensitivity, we had several questions asking about what elements TXRF is able to detect, what are the detection limits and how are they determined, and why is it difficult to detect lighter weight elements? So to help answer those questions, I wanted to spend some time with our detection limits. So here's a table highlighting which elements we can detect with our instrument and the typical detection limits for each element. These limits are in areal density with units of e to the 10 atoms per centimeter squared, and the detection limits for each element are variable between samples. They're dependent on a handful of things like the surface composition, how rough the surface is, and sometimes interference from overlapping elements with a large presence. For our instrument, we use a Rigaku 310 fab, which can detect elements between sodium and uranium using a combination of 3 beam energies from our tungsten rotating anode source. For elements on row 4 and downward, our detection limits are typically between 1 e to the 9 atoms per centimeter squared and 3 e to the 10 atoms per centimeter squared. And then for lighter weight elements, sodium, magnesium, and aluminum, our detection limits are typically around 20 e to the 10 atoms per centimeter squared, which you'll notice is higher than with other elements. There was a question asking why it was difficult to detect lighter weight elements with TXRF, and the answer to that question is kind of a mixture of a limitation of the technique and current tools. It's hard to get a strong low energy peak as an incident beam on the sample to excite lighter elements. And with the lower energy fluorescent X-rays, it's harder for detectors to pick them up as well. There's also a question asking if trace elements in quartz were detectable at ppm level, which is a little challenging to translate to areal density. But if we make some assumptions, then 1 ppm is about 2.5 e to the 10 atoms per centimeter squared. So depending on the element, there's a good chance that TXRF would be able to measure the sample. So there were a few questions asking about comparisons between different techniques. One technique that is often compared to TXRF is VPD ICP-MS, or vapor phase decomposition ICP-MS. This is another surface technique where an acid droplet is run across the whole surface of the wafer to dissolve the surface contamination. and then the droplet is analyzed with ICP-MS. BPD can achieve detection limits that are similar to TXRF, but choosing between the two will depend on the sample and the goal of the analysis. With TXRF, the analysis is non-destructive, and when mapping samples, it is able to give location-specific details of the contamination, like seen on the figure on the left. Some other things to consider too is if the wafer film or the surface substrate will go into solution. But yeah, by having this unique ability to see what the map of contamination looks like, it can be a huge help depending on your goal. Another question asked about what comparisons can be made between XPS and TXRF data for composition analysis. And while both can provide information about contamination, there are a few things to be aware of. Like Greg mentioned earlier, the depth of analysis can have a big impact. And between the two techniques, the depth of analysis may slightly differ. XPS has an analysis depth of 5 to 10 nanometers, while TXRF has a depth between 3 to 8 nanometers. The detection limits are also different between XPS and TXRF, with TXRF able to see to a substantially lower detection limit than XPS by several orders of magnitude. There may also be different sets of overlapping elements with each technique, which would lead to different interferences to consider. So speaking of interferences, there were a number of questions asking about if there were any limitations with different substrates that would cause issues with analysis. Questions like, is the technique able to measure silicon carbide wafers or gallium arsenide wafers? And what are some issues that make the analysis challenging? So I wanted to touch on what substrates TXRF could measure. So with TXRF, we can measure many common semiconductor substrates like silicon carbide, gallium arsenide, gallium nitride, sapphire, indium phosphide, and a lot more. Each substrate will have different substrate peaks. They'll appear at different energies. And here are a few examples of what the spectra would look like here. And in some cases, like with indium phosphide wafers, there are a few substrate peaks that overlap in energy with other elements like potassium and calcium and make detection of these elements difficult. But in most cases, such as gallium arsenide, gallium nitride, and silicon carbide, there's little interference with other elements. And one unique thing I wanted to highlight is with gallium arsenide and gallium nitride wafers. So in most wafers where gallium is part of the sample matrix, gallium will undergo some Raman scattering with the incident beam. So it'll absorb and re-emit the incident beam energy over a spread of slightly lower energies. That ends up creating an artifact hump right around here in the sample, in the spectra, near the incident beam. This area of the spectra is where we end up quantifying nickel, copper, and zinc, and we can account for these artifacts when working up the data. So going along with looking at substrates, there were also a lot of questions about which thin films TXRF can support. There's a lot of curiosity about gallium nitride films, which films can be measured, and what kind of crystal growth is supported. So with thin films, like with substrates, we're able to support many different types of films. Films like silicon nitride, silicon carbide, gallium nitride, and a lot more. And we can use TXRF to take a look at any of the surface contamination that may have happened from the film treatment. In this figure here, we have some example data from a wafer with a thin film of tin. And we can see on the right here, there's traces of iron and nickel that were present on the surface. So in most cases, we were able to measure films, and depending on the elements of the film, there may be some interferences to consider. But if there are any specific concerns, feel free to reach out to us and we can give an idea of what we can do. To answer a few of the questions about supporting gallium nitride films, yes, we can support them, and there are only minor issues from the gallium Raman artifact that I mentioned earlier. And in the types of films we analyze, it doesn't matter if the film is amorphous, polycrystalline, or epitaxial, we can measure it with TXRF. So speaking some more about our measurements, we had some questions asking about what the technique is capable of. So we can measure wafers with two methods. One method is to measure at 3 or so points to give an overall check on how clean the wafer is, or we can measure it in mapping mode, which we use to map the entire surface of the wafer. So yeah, we can cover the full wafer surface like with XRF. Which technique you want to use will depend on what information you want to know. So with XRF data, you can tell the film thickness and bowl composition. And with TXRF, we could measure and quantify the surface and film contamination. But yeah, so on the left is a scale map of what a 121-point map would look like on a 12-inch wafer. And the red dots are to scale with our spot size of 1 centimeter. And I'm happy to say too that with our instrument, we can provide 0 edge exclusion for 200 millimeter and 300 millimeter wafers. So we can measure and map right up to the edge of these samples. So speaking of samples, there were a handful of questions asking about what the sample size needed is and the limitations of what we can measure. So to give more information about these, for our samples, we can measure wafers and thin films only. And since the technique is very surface sensitive and the beam needs to reflect well off the sample needs to have a smooth, flat surface. We also run into issues with patterned wafers. The rough edges from the patterning tends to cause a lot of scattering, which can cause issues with probing deeper into the material than we'd like to see ideally. For wafer sizes, the smallest we can measure is a 50 millimeter wafer or a 50 millimeter square wafer piece. Anything smaller than that, and we will run into issues with getting too close to the edge of the wafer. And for sample thickness, the most we can allow is 1.5 millimeter thickness. If the sample is thicker than this, we run into issues with the sample stage and the detector height. So with the technique being so surface sensitive, I wanted to make sure to answer some of the questions we received on sample handling. With TXRF, we are very surface sensitive. We take a lot of precautions when handling samples. We always recommend that samples are sent to us vacuum sealed and are prepared in a clean room environment. We have our instrument in a class 10 clean room, and we will bring sealed samples as we receive them into our clean room before unwrapping them for analysis. For most wafers, we will use a vacuum wafer wand to handle the wafer and pick it up on the side that we aren't analyzing, so we can load it into our instrument. And for 300 millimeter wafers, if we receive them in a FOUP with the surface we want to measure facing the top, we can actually load that directly onto our instrument. So there's no need for any manual handling. But yeah, by doing these things, we're able to greatly minimize any contamination from handling. With many wafers we see, there's some typical contamination of sulfur, chlorine, and bromine from all clean room environments that's to be expected. But other than that, the environment is free from other risks. So to summarize a bit about the technique, with TXRF is an elemental survey technique that can quantify any surface contamination from sodium to uranium. It's very surface sensitive and non-destructive and has a 1 centimeter spot size. For our measurements, we can measure any specific locations that are of interest, like handling sites or contact sites, or we can map the whole surface of the wafer, tracking down specific areas of contamination or your end goal. For some of the limitations, we can often only measure polished, unpatterned wafers only. And in some cases, with certain substrates or films, there may be issues with interference we can try and work around. The smallest sample we can measure is a 2-inch wafer, and we cannot detect low Z elements like hydrogen through neon. So yeah, I hope I was able to show you something new or useful about TXRF, and I wanted to thank you for listening. Now to help answer some of your questions about RBS and HFS, I'd like to pass it over to Venkat.
Thank you, Louis. Before I realized my mic was muted in the introduction, so I would like to reintroduce myself. Myself is Venkat Vemuri. I'm working as RBS scientist at EAG a little over 6 years. So my background is in material science and ion beam analysis. Before coming to EAG, I worked as a researcher at Pacific Northwest National Laboratories. So we have received many questions regarding RBS, and in particular RBS and HFS. Here I grouped most of the questions and I'll try to answer them as detailed as possible. So in RBS HFS, we use high energy ion beam to measure atomic concentration of the thin films. When a high energy ion beam enters the solid or a material, a lot of things will happen. The ion solid interaction generates substantial information about the sample in various forms. Here, the ions are scattered back and X-rays are generated, and the material atoms are recoiled off, and gamma rays are generated, and nuclear reaction products are generated. So when the net energy change during the ion solid interaction is zero, that is called elastic scattering, and all these techniques fall under the elastic scattering. So when the net energy change is not equal to zero, delta Q is not equal to zero, or the interaction is exothermic or endothermic, that is when the nuclear reaction products will form and gamma rays are generated. So we use these phenomena in our lab to analyze the sample. Most of the time we use RBS and HFS, and these are the ancillary techniques we use to improve the results. So as I said earlier, we use high energy ion beam as an analysis probe in RBS and HFS and other ion beam analysis techniques. On a regular basis, we use 2.25 MeV helium ions. We also use proton beams and also deuterium beams for specialized nuclear reaction experiments. So we achieve this high energy ion beam using a particle accelerator. Ions are generated in an ion source at low energy, roughly around 25 keV. And these are accelerated in a high voltage terminal. The maximum voltage of the terminal is 1 million volts. And in the analyzing magnet, we monochromatize the beam and focus using beam optics and focus down to the sample that is situated in a high vacuum chamber. Here, I would like to take an opportunity to introduce two of our experts, RBS experts, Dr. Daniel Zeng and Dr. Bruce Rothman. Both have multi-year, multi-decade experience in ion beam analysis and surface analysis. They both have academic and industrial experience. So here is the schematic of RBS experiment geometry in our lab. So ions enter the sample at normal incidence. There are two detectors. The scattering angle is 160 for one detector, and this is another detector where the scattered atoms enter the detector at grazing incidence. The scattering angle is a little bit variable, 90 to 100. We can vary the scattering angle for this detector. So the detector measures both energy and also the yield of the scattering, like how many number of atoms are scattered back. So the energy of the backscattered particle carries the information regarding mass of the sample that is being scattered, and also energy, the depth at which the atom is located in the sample. So from the energy, we can get information of the mass of the sample, the target atom, and also the depth of the target atom. And from the scattering yield, the concentrations are calculated. This is a simple operation technique. So we have received questions regarding how RBS calculates thickness and density, and how accurate is the thickness value we provide. Here is an example of RBS spectra, that is platinum on silicon. So this is the platinum peak corresponding to the scattering peak corresponding to the platinum. And using this, the area of this platinum peak, we can calculate areal density of the platinum using this equation. This equation, in a way, is a simplified but final solution of RBS physics. Here we are solving RBS physics for the ion scattering physics. So area is the peak integration of the platinum. For example, an ith element is platinum, and area here A is the area peak integration of the platinum. Theta is the scattering angle, that is 160 degrees. Q is the total ion dose. Omega is the solid angle of the detector, and sigma is the scattering cross section of platinum. I'll discuss this about in the next slide. But here is interesting thing. Here we are calculating the areal density of the platinum. We are not sputtering, or we are not using any standards to calibrate. We're just solving the ion physics. So here, the interesting thing to note is like the atomic density and the thickness are connected in an implicit mathematical relationship. So one is needed to calculate the other. So during the analysis, we typically assume a density based on approximate materials inside, approximate concentrations of the material, and we calculate the thickness. Another important thing to know, so to calculate accurate thickness, we need density of the film or vice versa. So to calculate the density, we need accurate thickness that is calculated from any other technique such as cross-section TEM or cross-section SEM. So in summary, our thickness values are very approximate. They are as accurate as density we assume. So another important thing to note in here is we are obtaining areal density from first principles. We are not using calibrations, or we are not sputtering it out. So there is a question: when should we order SIMS, or when should we select SIMS or RBS and HFS? So if there are no suitable standards for SIM standards for your the material system of interest, or if you don't need any sputtering of the film, if you want to have a non-destructive film, no destruction of the film, yeah, you can select RBS and HFS in that scenario. So scattering cross section. Scattering cross section is a measure of probability of scattering events. In any solid, there is a lot of free space in there, so not all the ions enter into the film or the material will scatter out. There is some of the ions scatter out, and some of them pass through the sample and lose energy. So scattering cross section is a measure of how many atoms are, what is the probability of ions being scattered back. So that is dependent on atomic number and also the mass of the target atom, atomic number of the target atom. So here is the relative cross section of several elements with respect to bismuth, being the highest heavier element. So the relative cross section of all these elements with respect to bismuth. Here you see the relative intensity of scattering or scattering cross section is low for low Z elements, and the scattering cross section improves or goes higher along with the mass of how heavier is the element, mass of the element. So the detection limits dependent on the scattering cross section. So for low Z elements, like lighter elements, we have poor detection limits, like 1 to 10 atomic percent. For typically for Z number of less than 20, atomic number less than 20. And the detection limits improve as we go higher the atomic number. Heavier the element, the better is the detection limit. So RBS is very sensitive for heavy elements like gold, platinum, tungsten, bismuth, tantalum. So we have received many questions regarding hydrogen forward scattering. Hydrogen forward scattering is a sub-technique of elastic recoil detection analysis. So here we only the recoils here are helium and hydrogen atoms from the sample. This is also a first principles technique. So here we are not using any calibration standards. The helium ions enter the sample at grazing incidence, and the hydrogen and helium atoms are recoiled off the sample, and we strip the helium atoms using a helium stopping foil, and only the hydrogen atoms reach the final detector, and we count how many hydrogen atoms are received in here. So this is a accurate technique of hydrogen measurement in thin films. The typical material systems we encounter on regular basis is DLC films, low-K films, hard mask films, oxides, nitrates, whatnot, like all the films those are hydrogen bearing, we can measure. And HFS is the ideal measurement technique for ALD and CVD films. By the nature of the deposition, the ALD and CVD film always have hydrogen in them, so HFS is ideal technique for them. We have received questions regarding what is the detection limit. So the detection limit is 0.3 atomic percent, and maximum analysis depth is 500 nanometers. So this is the typical RBS and HFS spectrum for silicon nitride, hydrogen bearing silicon nitride. So we measure RBS spectrum, HFS spectrum separately, but on the same sample substrate. And these are fit together iteratively to get the final composition solution for silicon, nitrogen, and hydrogen. We have also received whether is there any technique that can do subsurface analysis of the films. Yeah, RBS is a subsurface analysis. By principle, it is not a surface technique. So here is the typical example of titanium and aluminum multi-layer stack. There are 10 pairs in here, 20 nanometer titanium and 20 nanometer aluminum. Yeah, you can see these fringes. These fringes correspond to titanium, and these are correspond to aluminum and titanium. So yes, RBS can measure subsurface and multi-layer stacks. So there are questions regarding what is the ideal sample configuration also, and what is the sample size minimum and maximum sample sizes. So minimum sample size is 5 millimeters for RBS and 1 to 2 centimeters, 1 by 2 centimeters for HFS. This is because both spot size and the measurement geometry. So for RBS, typically we use 2 millimeter spot, and for in special cases on we can lower the spot size up to 500 microns using special focusing apparatus. So, but on day-to-day basis, we use 2 millimeter spot size. So for that reason, we need minimum size of 5 millimeters and 1 to 2 centimeters for hydrogen forward scattering. And the maximum sample size is dictated by our substrate holder, that is 50 millimeters. Are we capable of full wafer? Yes, for RBS with certain limitations. So we can reach only certain spots. We have special apparatus to load full wafers, but we cannot reach all the area in the 12-inch or 8-inch wafers. So for HFS, full wafer analysis is not available because of the warpage of or bending of full wafers during analysis that causes errors in hydrogen measurement, because HFS measurement is a grazing instance technique. Regarding the analysis depth, beam loses energy as it goes through the material quickly. So for RBS, the maximum analysis depth is typically we suggest 1 micron. We can stretch up to 1.5 micron, but for hydrogen, the hydrogen beam enters the material at grazing instances. So the beam loses energy much quickly than RBS. So the maximum analysis depth is capped at 500 nanometers. So the typical film thickness is that we can measure is dependent on the analysis depth, that is 10 nanometers to 1 micron, and in case of HFS, 30 to 400 nanometers. So the depth resolution is not much great, not comparable to other techniques like sputtering techniques. It is depth resolution for RBS is 10 to 50 nanometers and 30 to 40 nanometers for HFS. Yeah, strengths regarding for RBS, it is a first principles technique. We are calculating accurate film composition by solving the RBS ion solid physics. We don't need any calibration standards. And in fact, RBS generates calibration standards for other techniques in some cases. not on regular basis, but if they require, we can generate that. RBS measures bulk composition of the film. It is not a surface technique. And we can measure all the elements from hydrogen to uranium. So this is large analysis area. The spot size, minimum spot size is 2 millimeters, and it has a poor depth resolution. Depth resolution is not much because of the ion scattering physics. Poor detection limits for lighter elements. As I explained earlier, we have the scattering cross section is low for lighter elements, so we have poor detection limits for these elements. And not every film or film stack is solvable by RBS physics. So we always suggest contact us ahead of the time to see the feasibility of the your analysis for your film stack. On regularly oxides, nitrides, carbon films, these are all we can do, but there are some special cases we receive film stacks, those are not suitable for RBS. We always suggest you to contact us beforehand. So in comparison to other techniques, RBS is not a spot depth profiling technique, and it is not a sub-technique of SIMS. It is a standalone technique, and it is not a surface technique. It's a bulk thin film analysis technique. RBS is suitable for thin films. We do bulk samples also, but as I said, the analysis depth is limited for top 1 micron. So we have received questions regarding some ancillary techniques of RBS, that's ion channeling, whether to measure the crystallinity of 3,5 materials. Yeah, we use ion channeling to see the damage in single crystal materials and epitaxial films. And also we can measure dopant substitutionality in lattice sites using ion channeling measurements. So we can extend RBS detection limits for light elements using nuclear reactions. For example, lithium, boron, carbon, nitrogen. These have poor detection limits for pure RBS technique, but we can extend the detection limits using nuclear reaction analysis. But these are case-by-case basis. We have to see the feasibility of film stack before we say yes for the analysis. So I thank you for listening to my portion of the webinar. Now I give floor to Greg Strassman.
Okay, thank you to all of our presenters, and I'm just going to wrap things up quickly. We want to give some time for answering other questions, so I'll wrap things up with a brief summary before we continue on to the questions. We'll go back to where we started, but now when you see this basic comparison chart, again, you have a lot of the underlying details behind these categories. Just to recap, while XRF and TXRF are both forms of X-ray fluorescence spectroscopy, the unique design of XRF instruments utilizing the grazing angle for the X-ray excitation leads to a very specialized application, the analysis of ultra-trace surface analysis residue on smooth, flat surfaces. And while the mechanics of generating data between XRF and RBS couldn't be more different, both techniques are excellent tools for thin film analysis. Okay, now we'll welcome all the presenters back and we'll answer more of your questions. So if you want to type more questions in now, I'll try to look at them and pass them forward. But in the meantime, I've also collected several of the questions that were initially submitted over the last few weeks that I can start with also while we await any new questions that start or to come in, I should say, come in live. So we'll start with a question for Luke. This is a question regarding XRF instrumentation. So what is the difference between EDXRF and WDXRF?
Yeah, sure. So let's just give a little background here. XRF instruments come in 2 varieties based on the system for detecting the X-rays. The first being energy dispersive XRF or EDXRF. This type of XRF uses a solid state detector, which is going to provide fast simultaneous detection of the elements. ED-XRF instruments have a high signal throughput, which makes it possible to operate at really small spot sizes, down to 5 micrometers or so in certain instruments, while also performing analysis fairly quickly. Now, wavelength dispersive XRF utilizes the diffraction of X-rays through crystals to disperse the fluorescent X-rays for detection. These crystals have known d-spacing, and when we consider Bragg's law, the photon energies can be measured based on those diffraction angles. Now, through the use of crystals, WDXRF has significantly better energy resolution and lower background than EDXRF. And it also is able to measure elements down to boron and in specific applications beryllium. Whereas energy dispersive XRF, typically the lowest it can get is sodium. WDXRF has the best accuracy and precision, but if we're trying to do a full elemental survey, it's going to take a little longer than with EDXRF.
Okay, thanks, Luke. And we have limited time, and I've got more than one question available for all of the experts, but I'm going to try to cycle through alternating, so that we can get some in the available time we have. But just as Rena said, all of these questions will be answered eventually at a later point within the next week or so. But I have an RBS question for Venkat. What's the detection limit of halogens in RBS?
Yeah, like we can detect fluorine, chlorine, iodine, and also so the detection limits dependent on as I said in the presentation, the detection limits dependent on the atomic number. So fluorine, we have a decent detection limit of 2 to 3%, but for iodine, chlorine, we have much better detection limits. So for example, iodine, we have 0.03 atomic percent. For chlorine, we have 0.5 atomic percent detection limits.
Okay, very good. Thank you, Venkat. And now for Lewis, what issues come up with TXRF if the sample is not smooth enough?
So if the sample is not smooth enough, the X-ray will strike the sample and you'll see a lot of scattering. With that scattering, it will cause a lot of things to saturate the detector. So you'll end up seeing a higher dead time. And like with the higher dead time, you usually see higher detection limits for that sample. If it's really rough, and even just like running it at full power, it's just has that overly high dead rate. We can end up like lowering the power and then adjusting our calibrations, but then that may raise the detection limit a little bit, but still pretty good detection limits. But yeah, it's something we kind of look at with each sample as we get the data and kind of adjust from there.
Okay, very good. So Luke, can XRF be used to identify formation of intermetallic layers in a stacked layer structure?
Yeah, so as we discussed earlier, XRF, it can measure composition and thickness of the thin films, but yeah, unfortunately, we can't identify intermetallic layers, mostly because it's just not segregated enough like we would find in thin film stacking.
Okay, very good. So we have time for maybe a couple more questions. Let's see if what we got here. Can we measure, or Venkat, can we measure the concentration of oxygen in material with RBS?
Yes, we can. We can measure oxygen in the oxide materials, but the detection limit will be higher. For example, detection limit is dependent on, as I said earlier in the presentation, like oxygen has a lower cross section. So, and also if the oxygen is it depends also on the substrate material. So the substrate material can saturate the oxygen signal. So the detection limits are typically higher, like 4 to 5 atomic percent if it is if the substrate is heavier than oxygen. For example, silicon, is the substrate of that film. We can measure the oxygen, but the detection limit will be higher, 4 to 5 atomic percent.
Okay, very good. Thank you. And we'll have one more time for one more question. We'll hit a live question. And again, it's going to be an RBS question. I'll read it verbatim as it's written. Regarding RBS, at the end, you mentioned ion channeling, especially for determining information on, say, substitutional dopants. Can you elaborate a bit more on that? And could RBS give info on substitutional versus interstitial dopant concentrations?
So the basic principle of ion channeling is we align the substrate along the axis of the ion beam. So the ion beam can traverse through those ion channel if there is no obstruction that goes through the ion channels and there are no scattering events. We have a less signal. So if the ion beam encounters substitutionally doped ions or atoms in the ion channels, the scattering events will happen. So by comparing the bare or pure material with the substitutionally doped material, we can see the difference and calculate how many substitutionally atoms are there inside the ion channels.
Okay, very good. I think that's going to wrap up. We're just past the noon hour, so we'll move on to wrap things up. One last slide for me to summarize, and it's why would we choose Eurofins EAG for our analytical requests? And there are several reasons as listed here, but I think it's important to state right at the top that client confidentiality is core to our business. We fully understand that much, if not all, of the stuff that's being worked on in your individual labs is highly confidential, and you don't want that information to leak out when you're doing research development or at any stage of a process of your samples. We're also a global leader in materials testing services with a broad range of instruments and expertise that leave us poised to take on even the most challenging materials and engineering related issues. And also, it's good to point out that at EAG we have various certifications, accreditations, and regulatory approvals and/or licenses to support our clients' needs. So with that, I'll turn this back over to Rena to wrap things up.
Thank you, Greg, and thank you to all of our experts for this robust discussion and presentation, and thank you for everyone for attending today's event. If we didn't get to your questions today, we'll be following up with you soon, and if you have any other questions, please send in your questions to the email address on the screen. That is customerservice@eurofinseag.com. Also want to mention that I have added a few links to our resources in the chat window, including next week's Ask the Expert event on failure analysis of electronic devices. So please check those out. And once you leave today's webinar, you will receive a survey on the presentation, and we would appreciate your feedback. On behalf of Eurofins EAG Laboratories and our experts, thank you for joining us today, and have a great rest of your day.